continuous type problem is here. You have a continuous type with PDFF and then capital F as the CDF. You have your problem like this. In particular, you have your IC constraint and your IR constraint. Okay? And with so many constraints, you are not able to do anything. So we need to first reduce these constraints. Okay, IC and IR. We need to somehow remove something that are not required for this problem. Okay, so as usual, step 1 is to remove some IR constraints, in particular those IR constraints that are not for the lowest type. So all those IR constraints are redundant except the one for the lowest type. Okay, so let's see why this is true. Suppose I have a theta that is greater than or theta lower bar. In that case, this is the left-hand side of the type theta agent on the right-hand side of its IR constraint. Okay, its earnings. It's going to be greater than or equal to what he may get by pretending to be the lowest type. So this is from your IR constraint, IC constraint. From your IC constraint from theta to theta lower bar. Okay? And then from here, because theta is greater than theta lower bar, and the V function eventually will be non-negative. So that's why from theta greater than theta lower bar, you have this. Okay? You have your second inequality. And then finally, because you have the IR constraint for the lowest type, this is non-negative. Okay? So as long as you guarantee for the lowest type, he can earn something, then everyone will be happy as long as you satisfy all those IC constraints. Okay? So this is our first step. We can eliminate all those IR constraints with only the last one remains there. Okay, our second step will be much harder. It will state that all those IC constraints can be replaced by these two sets of constraints, monotonicity and the local IC. Okay? That means later what I will do is to remove all those IR constraints, but add these two sets of constraints into my problem. I'm going to show you that the problem will remain the same. The constraint and the feasible region is actually the same thing. Okay? So let's see this. First, we need to explicitly tell you what are IC, local IC, and the monotonicity. Let's define this. Define this W function as the agent, the type theta agent's payoff. Okay, type theta agent's payoff when he pretends to be theta hat. So he is of type theta, but he pretends to be type theta hat. In that case, we call W as his payoff when he do this pretending. Okay, here it will be easier for you to have a usual way to denote these two notations. Theta is typically called the true type. Okay, indeed I know what I am. And theta upper bar, theta hat is the reported type, or simply the report. Okay, you know this is a direct mechanism. The principle is asking the agent to report the type. And then the principal will ask you to give a quantity, give a payment. Yeah, exactly the QT pay. So the agent is deciding what type to report. And the IC constraint says that among all those possible types that you may report, you want to report your true type so that you can maximize your payoff. Is that clear? This is IC constraint, asking all the agents to tell the truth of the IC constraint. Okay, so now the other two. Monotonicity is similar to what you have learned from discrete types. It says that when theta becomes larger, the quantity should become larger. Higher types should consume more should get a larger quantity. Okay, for all the types, Q prime, or the first order derivative of Q, should be non-negative. Okay, so now let's think, what is local IC? Here, local IC says that I don't need to satisfy the IC globally. I need to satisfy only the local IC constraints. So let's see what's this. Here it will be easier to draw a graph to help you understand this idea. Suppose this is theta, and this is your W theta hat. Okay, I mean this is theta hat. Suppose the agent is thinking about choosing a theta hat to maximize his true type, and let's assume his true type is here. Okay. In this case, we know it is not very good. It is not very good to tell the truth, because if you tell the truth, this is what you earn. But if you do not tell the truth and it lies here, okay, it's possible to get more by telling a lie. Okay, so in this case, global IC is not satisfied. But we say at least local IC is satisfied. Okay? For those neighboring types, theta is optimal. Yeah. So that's the meaning of local IC. And indeed, exactly that means the first order condition needs to be satisfied. Okay? At this point, you need to satisfy your local. If you want to have local IC constraints, that means you need to satisfy the first order condition. So let's see what's this. I'm looking for a theta hat. Okay, this is my variable. Looking for a theta hat to maximize this. So I do a first order derivative with respect to theta hat. And then if I plug in theta, okay, sorry, I made a mistake. If after the differentiation, I plug in theta hat as theta, I choose theta to be my report, then I should get 0. Okay, the derivative should get 0. That means I satisfy the first order condition, and theta is at least a local optimum. Okay, in this case, I know I should take the first order derivative with respect to theta hat. So when I do this, okay, theta is a constant. Okay, theta is constant. So first v prime, first order derivative of v, and then chain rule you have q prime. This is hat. Sorry, hat. And then for t you get t prime. Okay, first order condition. Then you plug in theta hat back. Plug in theta back into theta hat, and then you get equals 0. This is your local IC constraint. This should be satisfied for all the types. So here, this proposition is telling you that you don't need to worry about global IC as long as you have local IC and monotonicity. Then these two parts are equivalent. So I need to tell you why this is true. So this is an if and only if statement, so we need to prove two directions. Let me do the first one. So first of all, I'm going to show that if you have IC, then you have the other two. So to do this, let's take a look at this payoff function, and then do the first order derivative and second order derivative. This is the first order derivative of your W function. Indeed, it's here. You have did that once. But here we need to do it twice. Okay, we need to do it for one more time. take the first order as the one more time of derivative with respect to theta hat, we can see that okay, here theta is a constant again. Here you need to apply the product rule. This guy one more time, and then another term q prime enters here, so you have a square. Or you keep this the same, but you differentiate q prime one more time. And finally, t must be differentiated one more time. Okay? Because you are looking for the maximum point. So you know your second order condition, second order derivative must be non-negative, non-positive. Okay? This guarantees you to have a downward curvature at this point. This is an optimal, a maximum solution. If you have IC, these two things must both be true for all types. Okay? Okay. If that's true, then immediately you have your local IC, right? Oh, this part gives you local IC, right? Because naturally, global implies local. So you have local IC. Now let's see how may we find the monotonicity condition. Okay, so we need to do another differentiation here. Okay, let's look at this equation. This equation is your local IC constraint. If we differentiate it again, what will happen? This says a function equals 0. We take the first order derivative with respect to theta at the both sides. Okay, well, let's see what will we get. Here, what's the difference is that here theta, 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 we have a function with 3 components of theta. So when you apply the product rule, this term will become 3 terms. Okay, so let me write it down. Okay, this is what you will have when you do the differentiation at the left-hand side. For the right-hand side, 0 gets to 0, so you have this equality. Okay? It's tedious, but this tells us a lot of things. In particular, we can compare this with our second-order condition here, second-order derivative here. If you do a comparison, you can see this part, and this part, and this part. They are identical for the both sides. And we know these 3 things together are non-positive, right? So that means this term must be non-negative. Is that okay? If this is true, then further observation tells us that okay, this is V prime. V prime is the slope of your V function. Your V function looks like this, right? So your slope must be non-negative. Oh, so eventually you know, okay, Q prime must be non-negative, and you have your monotonicity condition. Okay? Let's complete our first direction from IC to the other 2 things. Now we need to show that from the other 2 things we have the IC constraint. Okay, so now I want to do local IC plus monotonicity gives us the IC constraint. Okay? So I'm saying that if I have these 2, I have IC for forever. Yeah. So now let's assume this is not true. Okay? I have local IC and the monotonicity, but I do not have IC. In that case, I know there is some guy. And what happens to this guy? Lying is better than truth telling. assuming IC is not satisfied. So there is one guy lying is better than truth telling. In that case, let's write down the expression here. Okay, this is what you may get by telling the truth. And this is what you may get by lying. Okay, we have this inequality. And then this inequality, or we should say the difference between these two sides, can be written down as an integral. Okay, so to remind you, suppose you have two functions, f of b and f of a, you want to find the difference. What you have is actually an integral of the differentiation. Okay, this is what you have. The difference is the integral of differentiation. But here I want to ask, what's the difference from the left to the right, from the right to the left? Okay, and then I know, oh yeah, it's indeed this guy. Okay, one thing is changing is this from theta to theta hat. Okay, from theta to theta hat, and then we take the differentiation to the inside of an integrand, and then do an integration. Okay, this will be greater than 0 because the right hand side is greater than left hand side. Okay, here one thing to remind you is this happens if theta hat is greater than theta. Okay, if theta hat is less than theta, then you have the reverse thing. But you can do that, and it's the other part of this proof. But we're not going to do that because everything will be identical. Okay, so assume theta hat is greater than theta, then we have this expression. Okay, that's something. So yeah, let's have something there. Put that in mind, and let's consider what will you have if you have local IC and the monotonicity. I'm going to show that local IC and the monotonicity will find something, will find this thing impossible. Okay, here, suppose you look at the true type and all those types that are higher than the true type. Then you know several things. First, from monotonicity, this differentiation must be non-negative. Also, how do you get this? V is non-negative, right? And the theta is less than x. So you have this. Yeah, so you have these two things. Combining them, you're going to get this. Okay, I'm imitating what we have here. Okay, you can see I'm written down exactly the same thing as we had with the thing we supposed to be not true. Okay, what will happen here is that this thing is going to be less than or equal to a simple replacement. Okay, from here to here, only one thing is different from theta to x. I know this term is less than the replacement from theta to x. So this comes from our second inequality. Also, q prime is non-negative, so it's good. This inequality will be retained, and we have this less than or equal to condition. But now how do we apply local IC? Exactly, local IC is telling us that this integrand is 0, right? This is exactly the local IC condition for the type X agent, and that must be 0. So you have shown that if these two are true, this particular integral must be non-positive. But you need that integral to be positive so that people have incentives to lie. Yeah, so which is impossible. Okay? So that's why local IC and monotonicity implies IC. So now we have shown that these two parts are equivalent, and with that we're going to eliminate those constraints problems to the reduced one. And in the next video we're going to solve